Okay, good morning, dear students. A very good morning to you all. You are welcome back to CHM 101 class. I hope you had a beautiful night rest. And today we will just continue from where we stopped yesterday. You will recall that yesterday I started teaching you enthalpy. So that is just where we will continue from today. So yesterday I started by explaining what enthalpy is, and I told you that it's a state function. I reminded you of the equation that describes enthalpy as dependent on the internal energy, pressure, and volume. So we also discussed the enthalpy changes in terms of the enthalpy of the initial states and the final states. The difference makes the change. And we looked at enthalpy change as enthalpy of products minus enthalpy of reactants. And we describe endothermic and exothermic reactions in terms of enthalpy. So today, I will just continue from there. And from what we have here, you can see that we are beginning to talk about enthalpy of reaction. So when you have enthalpy of reaction, that means you are talking about reactants and products being involved. When you need to add energy to a material to change its phase from liquid to a gas phase, for example, the amount of energy that you put in is what we call latent heat of vaporization, because you are changing the state of that substance from liquid to gas, forming vapor. So that makes it easy for you to know. Enthalpy of vaporization, that is what we call it. And there could be other phase transitions similar to that. You can have enthalpy of fusion. That is the amount of heat change that is involved when you change the states of a substance from solid to liquid. And enthalpy of reaction is the enthalpy change accompanying a reaction represented by a balanced chemical equation. Don't forget, I told you yesterday that for enthalpy and even for entropy, for free energy change, all of these things, we must work with a balanced chemical equation. So for any physical or chemical process where there is an enthalpy change, you can have the reverse as well. And the reverse will be accompanied by the reverse enthalpy change sign. So where you have, for example, enthalpy of fusion for solid to liquid, if you reverse it, the process, you are moving from liquid to solid, then the sign will change. So you can see the example that I gave here. You have carbon in solid state reacting with oxygen gas to give CO2. And the enthalpy of the reaction is minus 394 kilojoule per mole. If you reverse that process, that means you have CO2 giving you carbon and oxygen. Enthalpy is still the same, but the sign is different. And that makes the change. So that change is accompanied by this change in sign. So which means that while one is endothermic, the other is exothermic. So you need to bear that in mind as we go on. There are still other things you need to bear in mind. Enthalpy change can be related to the number of moles of each reactant. And this is what we mean. The example that I've given here is to show you that if you have chromium, 4 moles of chromium in solid state reacting with 3 moles of oxygen gas to give you Cr2O3, the enthalpy change for that process is minus 2256 kilojoule per mole. So how do we write this appropriately? To write this appropriately, you can express it for 1 mole of Cr2O3 that is formed. And what that means is that for you to have that, it means we divide this one by 2. Once you divide this one by 2 to have 1 mole of the product, then you will have to divide all these coefficients by 2. So the coefficient of the stoichiometry divided by 2, you now have 2 of chromium, 3/2 of oxygen, and 1 mole of Cr2O3. So you will not be able to leave the delta H as the same because you have changed the number of moles involved in that reaction. So this also will be divided by 2, and that is why we have minus 1126 kilojoule per mole for the second reaction. So the stoichiometric coefficient of the reaction in 2 is a fraction of what you have in reaction 1. And so delta H value will also change by the same factor by which you have changed the stoichiometry of the reaction. Also, the phase of the reaction really matters when you are determining delta H of any reaction. The phase or state of each substance, be it liquid, gas, or solid, taking part in the reaction must be specified. So how do we mean? If you have carbon, which is graphite, and oxygen, which is gas, you have to state their state because the enthalpy of formation of each state is different. So you can see that in this reaction, what you have is delta H equals minus 394 kilojoule per mole. And how do we know that delta H depends on the state of the substance? Look at the example that I gave below. In the 2 cases, we have water formed, but the first reaction shows water is in liquid state, whereas the second reaction shows that water is in glacial state. And because of this, you will see the change in enthalpy, they are not the same. Don't forget, this is not about the sign because we are not reversing the reactions, but here the state matters, the state of each substance. And that is why delta H for the formation of liquid water is minus 286 kilojoule per mole, while the delta H for the formation of 1 mole of H2O is minus 242 kilojoule per mole. These are the things you must know as we go on in the course of this discussion. So let's take a few examples. The first example here says how much heat is evolved when 500 kilogram of ammonia is produced according to the following equation. N2 plus H2 giving NH3. The first thing you will do all the time, like I told you, is to balance it. But interestingly, this has been balanced for you. But always endeavor to examine it. Now, delta H given here is minus 91.8. I don't think my pen is writing well, so let me use my finger. Skipping. So this is minus 918 kilojoule per mole. So you've been given the atomic masses of the elements involved, nitrogen and hydrogen given. So how do you solve this problem? It's very simple. The first thing you need to know is to bear in mind that this is giving you 2 moles, and the 2 moles you are getting it from 3 moles of H2 and 2 moles of N2. So the number of moles of NH3 in the substance that you have been given, you were given that substance in kilogram. So because you were given in kilogram, your coefficients of the stoichiometry will matter. So you need to know how many moles of ammonia is in that 500 kilogram of ammonia that was produced. So if you determine the number of moles, that is mass over molar mass of NH2. So once you do this, you obtain the molar mass from the atomic masses that you have been given. And then that gives you 17 grams per mole. Skipping. Okay. So we can see that mass is given in kilogram, and the first thing to do for the unit to be easy for you to handle is to convert it to gram. And so the number of moles that you have in 500 kilogram is here, which is 500 times 10 to the power 3, converting it to gram, divided by 17. So you really do not have any problem with this question. The number of moles has been calculated for you. So then, if this is the number of moles you have, then you have to come back to the equation and look at what you had. 2 moles gave this amount of heat, evolved that amount of heat. So you have negative energy, enthalpy that was produced. So what then will 2.94 times 10 to the power 4 mole of NH3 give? So that is how we calculate it, because we know that if 2 moles is giving 91 minus 91.86, then 1 mole will give minus 91.8 kilojoule per mole over 2 moles. And of course, in the course of doing this, some of the units we cancel out. This we cancel out this. And then you do the multiplication, and that is the answer. It's simple and straightforward. So you work from mass to number of moles, and then you compare the balanced chemical equation to know how much heat will be evolved by that mass. So then, another example that I have here, okay, I think I only put one example for you. You will have some exercises at the end of this class. So let's talk about the change in enthalpy and the standard enthalpy of reaction, or change in standard enthalpy of reaction, and then the standard states. I remember somebody was asking me a question yesterday about the standard states of oxygen, why the delta G standard was 0. And I explained it in the notes, and you will come across something similar now as we go on. So listen very well. So for delta H of reaction, we also go back to what we have known. Let me use the previous slide, which is blank. So we know that delta H is going to be delta H, of course, summation of all of the number of moles that is present for the sorry, let me come around and erase this. So you have delta H, just like we did for entropy. For the reaction, is going to be the summation of all the changes that you have. For products first, minus the summation, bearing in mind the coefficients of that reaction. Sorry, I'm not sure I'm getting so good with this. Delta H of reactants. Sorry, I will get used to this, but let me just go back to where the equation is so as not to waste our time. So this is what you have for the reactants and for the products, similar to what we did for entropy and for free, for entropy and for entropy and for the free energy. So if you look at this, we need to consider standard states. For standard states, we will work with this in standard states, and then this will also be in standard states for you to be able to say all of the reactants and products with the change in enthalpy must be in standard state. So what do we mean by standard state? The standard state of a substance is the pure substance in a specified state. It can be solid, it can be liquid, it can be gas at 1 atmospheric pressure. So there are standard conditions which you must bear in mind. For gases, is at 1 atmosphere pressure, or 10 to the power 5 Pascal. And for solution, it must be in unit concentration. And when you are dealing with substances, you must be talking in terms of their standard states. There are stable states, there are more stable states in which they exist. And so the standard enthalpy of a reaction, or the change in enthalpy, is the standard heat of reaction or standard enthalpy of a reaction. And like delta H also, it measures the enthalpy change for that reaction. So when we say standard state, then we must indicate the sign, and it means that the reaction is taking place at 25 degrees Celsius and 1 atmosphere for the reaction itself. If you are measuring delta H, then measuring it under standard conditions will allow us to have the ability to relate one value of delta H to another, since all of them are occurring under the same condition. So this is the advantage of using the standard change in enthalpy, because it allows us, when you have reactants and products, all of them in standard state, you can relate one to the other freely without having to determine whether it's in standard state or not, or converting or calculating until you are able to obtain the enthalpy in standard state. This has a lot of advantage as we go on to see the calculations that are involved with enthalpy change. I want to pause at this point and give the code for today's class. The first code will be given now. Please get ready to take the attendance code. The first attendance code for today is GM92S. G, that is general. M, mathematics. Figure 9, figure 2. S for standard. GM92S. Please submit your attendance code at this time. You don't have to type it here. So, we need to look at the enthalpy change that accompanying a change in states, and there are quite a number of them. And this is one advantage of enthalpy. You can relate one to the other. So when we talk about the enthalpy change when 1 mole of a substance melts, we are referring to enthalpy of fusion or enthalpy of melting. Enthalpy of fusion or enthalpy of melting, that is the enthalpy change when 1 mole, bear in mind it is 1 mole of the substance that is melting. If you have ice will melt to give you liquid water. Delta H of fusion is 6.01 kilojoule at 273.15 Kelvin. So what about freezing? Because we know that that same water can change its state from liquid to solid. So the enthalpy of freezing, delta H freezing, is that enthalpy change when 1 mole of a substance freezes. And like I said earlier on, it's possible to go from solid to liquid and then from liquid to solid. That is a reversible process. And that is why delta H freezing is going to be the negative of delta H fusion. The two states can be reversed. So it becomes a negative value of what we have for fusion. The third one is enthalpy of vaporization, and that is the heat required to vaporize 1 mole. Please always bear this in mind, 1 mole of a substance. And that vaporization is delta H vaporization, which is delta H of vaporization minus delta H of the liquid. And for 1 mole of water, you have delta H vaporization to be equal to 44.0 kilojoule at 298 Kelvin. For condensation, it is the opposite of vaporization. And for sublimation, you're going to have two steps that will be involved. For sublimation, it means we are going from solid to gas. And so the delta H of vaporization plus delta H of fusion is what gives you the enthalpy of sublimation. So you need to know all of this as you apply them later. Now, heat, like I told you, is I told you earlier on that we can refer to delta H to be equal to Q. That is, we can express it as Q. If we express it as Q, it then means that if you express delta H as Q, I told you in the last class that Q is the same thing as heat. So heat and enthalpy can be related together. And so temperature is what plays a major role here. So when you increase temperature, the amount of molecular interaction also increases. As you increase temperature, it means you are supplying more energy to the system and you are increasing the intermolecular attraction or interaction. So as the number of molecular interaction increases, then you increase the internal energy of that system. The internal energy, which is U, as it increases, then you increase delta H, because you know that delta H, H is actually U plus PV. So as you increase temperature, what we are saying is that you increase H in the overall. Now, for any material that you are supplying heat to, there is a property we refer to as specific heat capacity, and that is the heat required to raise the temperature of a unit mass. Here is a unit mass of the substance, and you raise it by 1 degree Celsius. So that is the amount of heat that is required to raise the temperature of a unit mass of substance by 1 degree Celsius. That is the specific heat capacity. And it can have either of 2 units, joule per Kelvin per gram or joule per degree Celsius per gram. How do we determine specific heat capacity? Specific heat capacity of any substance or any material is the heat capacity divided by mass. Remember we said is the amount of heat that is required to raise 1 unit mass. So that is what is reflecting in this equation to get you the unit mass. Specific heat capacity will be heat capacity divided by mass. Heat capacity itself is heat or quantity of heat divided by the change in temperature or rise in temperature, and that is Q over delta T. So if you combine equations 1 and 2, you will obtain the equation that is here, which tells us that Q is equal to mc delta T. Q is heat, M is mass, C is specific heat capacity, and delta T is the change in temperature. So how do we apply this? Let's take a quick example. Water has specific heat capacity of 4.18 joule per Kelvin per kilogram. 100 grams of water rise in temperature by 2.0. The question is that calculate the heat quantity absorbed by water. calculate the heat quantity absorbed by water. So it's easy because we have been told that there is a rise in temperature. That tells us that it's absorbing heat. And heat in this sense is going to have a positive value because heat is not lost, heat is absorbed. So for that, even though we have not put a positive sign here, it is implied because heat is absorbed. Don't forget what we said earlier on about enthalpy and about enthalpy in terms of exothermic and endothermic reaction. And even for substances that absorb heat or that releases heat, you can have Q change its sign from positive to negative. So if heat is absorbed, then Q has a positive sign. So if you apply the expression, well, somebody may say, oh, but what we showed us earlier on is capital Q. Both are acceptable. You can use capital Q and you can use small letter q. So whichever one you choose will be fine, but just be consistent when you are making your calculations. So if you look at what we have, substituting all of this value, very straightforward, we obtain our answer, which is 836 joule. Don't forget some of the units we cancel out. Oh, apologies, some of the cancellations actually jumped. But let me show you what to cancel. You cancel G here and per gram here. They will cancel out. Per Kelvin here, we cancel out Kelvin here. And so you are left with Q in joules. So what you have is 836 joule. Then the other example, 293.7 joule of heat is removed from 5 grams of aluminium, causing the temperature to drop from 82 degrees Celsius to 19 degrees Celsius. What is the specific heat capacity of aluminium? So if you look at this question, it's a bit trickish. All you need to do is to take a little time to understand it. If you are saying that you are removing heat from aluminium and you are causing the temperature to drop, Q is still positive. So at the end of the day, you use the same equation like we used earlier on, but the difference is that here, what you have the mass, which is 5 grams, and C is what you are calculating. Now, the difference in the temperature, you have been told that there is a decrease in temperature, and usually delta T is obtained by looking at the final temperature minus the initial temperature. So if you convert this, if you convert the first temperature, the initial temperature, because we're told that it dropped from 85 to 19. This is the final and this is the initial. So this is how you obtain delta T. Delta T is T final minus T initial. And by the time you do all of your substitution, you find out that the specific heat capacity of aluminium will be staring at you. And the value is 0.89 joule per Kelvin per kilogram. Per gram in this case. So I want to give you the second code before I continue, but let me quickly see if you can take the code now. The second code will be given now. You should get ready before I attend to the next slide. Second code, LNM ZB. They are all letters this time around. All are letters. L for leopard, N for new, M for mathematics, Z for zebra, B for ball. L N M Z B. I want to believe we all got that. L for leopard, N for new, M for mathematics, Z for zebra, B for ball. B for ball. Okay. So while you are submitting your second attendance code, we will be going back to the class. So I have a third example here, and I'm sure with all of these examples, you'll be home and dry with calculating specific heat capacity of any substance. In this example, I've given you 50 grams of an unknown material, 50 grams of an unknown material at 200 degrees Celsius was added to 100 grams of water at 25 degrees Celsius. The final temperature of the mixture was 41.8 degrees Celsius. What is the specific heat capacity of the unknown material? So if you look at what we have here, there are two materials. One is water, or two substances. One is water, the other one is an unknown material. And that material is at 200 degrees Celsius. You don't know that material. And then you had 100 grams of water. Water was at 25 degrees Celsius. So which means that you were bringing in a very hot material and putting it into cool water at 25 degrees Celsius. The final temperature of the mixture was said to be 41.8, which means that you have raised the temperature of water at the end of the day. So what is the specific heat capacity of the unknown material if the specific heat capacity of water is given as joule per degree Celsius per gram? So what you need to do is to look at the conditions that you were given. You were given a metal at 200 degrees Celsius, and then you had a final temperature of 41.8 degrees Celsius. You were also given water. The metal is at 200, water is at 25, and then you came to a final temperature of 41.8 degrees Celsius, which tells you that water has increased its temperature, okay, which means that it has absorbed heat, and so Q will be positive. This the temperature has reduced in this case, and because the temperature has reduced, it means that it has lost heat. So Q will be negative. And for these two set of materials, you need to bear in mind that they reached a point of equal temperature. And so the heat change involves an exchange between the material and water. So you have to think of water and you have to think of this material. But like I said, one of them, we have negative value, that is the material, and that is what I put here. The other one, we have a positive Q. So they have come to an equilibrium temperature. Then all you need to do is to use the same expression for Q for each one of them, and then substitute the mass, the specific heat capacity, and then calculate the change in temperature for each of them. So if you do this very well, you will realize that the material, which is 50 grams, okay, is the 50 grams has been substituted. For the material, we do not know the specific heat capacity, so C is the unknown. Now, for the material that we do not know its specific heat capacity, the final temperature was given as 41.8, and the initial temperature was 200 degrees Celsius. So you have to put that correctly. But when you come to the side of water, you will find our mass is 100, specific heat capacity is known, which is in per degrees Celsius. That is why we are not converting it. We want to maintain this unit at the end of our calculation. So you leave it in degrees Celsius. At the end of your calculation, you will obtain C in joules, 0.8895 joules. You are free to make that calculation yourself and you will find the answer to be correct. So the unit of the specific heat capacity, this is not well put. The unit is actually in joule per degree Celsius per gram. So that is what you have. So this is not this actually should not be there because we have already removed all the units. So when you get it, you find that this is the final answer. I want to believe that that is clear enough, and you can practice questions if you go to this website that I've provided here. You can take your time to go over this lecture in the archive and write out the links, and you can practice more questions. So how exactly do we measure enthalpy changes? We've been talking about enthalpy changes for change of states and for reactions. How do we measure it? There are two ways to go about this. Generally, what we use is called a calorimeter. You can have a simple calorimeter like the example that I gave here, and you can have a bomb calorimeter. A bomb calorimeter is a small laboratory apparatus that you can get, and inside of it has all of these components: a thermostat, a thermometer, a stirrer, ignition wire, oxygen, atmosphere, and then you put the sample in a cup. But for the very simple ones, which you can do on your own and you can experience in your part 1 or part 2 practical, you find it simple, like setting up a burner and putting a thermometer in a beaker, or maybe a styrofoam calorimeter can also be used, and then you can set it up to see the heat exchange. So measuring enthalpy changes of combustion is one way that you can use to determine enthalpy changes. And then you can also measure enthalpy changes of reaction. You can use the calorimeters like I explained. So if you look at a simple laboratory calorimeter, you can use what we call coffee cup. I'm sure you all know coffee cups, styrofoam cups. Sometimes you can double them or make quite a number of them to retain heat. That is essentially what they do, so that you are not losing heat in the process of the reaction. And then you can measure the temperature when you set it up properly and you put a thermometer. So what is done is to put one of these reactants in the calorimeter or in the coffee cup calorimeter. So when you put it there, you measure the temperature, and then by the time you introduce the second reactant, if heat is being generated, you will see that the temperature reading on the thermometer is going to go up, and you can use that to obtain your T initial and T final. And of course, for those cups that are made of styrofoam, they are very good insulator. They will lose little or no heat. But you can be sure that the heat that is lost by the solution will be the same as the heat that is gained by the calorimeter. So the calorimeter is what holds the reactant, or in the container in which the reaction is taking place. So when the reaction is taking place and heat is lost, what absorbs the heat is the calorimeter. So we can determine the heat capacity of the calorimeter from that simple experiment. And the heat capacity of the calorimeter will be the amount of heat absorbed by the calorimeter by unit change in temperature. So that takes us back to the equation that we used earlier on. So that is how you can measure heat change in a reaction. Now, standard enthalpies, they vary. Like we talked earlier on for phase changes, enthalpy of fusion, enthalpy of vaporization, sublimation, and so on. For reactions, the experiment that I described here using coffee cup can be used for reactions. Don't forget, And for those reactions, we can begin to look at different types of reaction. For example, you can have a neutralization reaction. So for a neutralization reaction, if you set it up that same way, the standard enthalpy of neutralization is the heat evolved when 1 mole of hydrogen ion, which will come from an acid, reacts with 1 mole of hydroxyl ion, which is coming from a base, to produce 1 mole of water under standard conditions. So the first thing is there is standard condition, which is 25 degrees Celsius. Which is standard solution of 1 molar. Sorry, you use standard solution of 1 molar. And so when you have the reaction between acid and base, you know that that is a neutralization reaction. And it means that you have hydroxyl ion and hydrogen ion coming together to form water. So the H plus is coming from here. So you have H plus from here because in solution, this is going to ionize. And then you have Na plus and OH. So what combines in the process is the hydrogen ion and the hydroxyl ion to give you 1 mole of water. So bear in mind, it has to be 1 mole of water. And so the standard enthalpy of neutralization is minus 57.3 kilojoule per mole. So when you carry out your experiment, that is the value to use. And then there's also the standard enthalpies of formation. What do we mean by standard enthalpy of formation? It is the enthalpy change. Enthalpy change. Don't forget, delta means change. Enthalpy change. When 1 mole of a compound is formed from its constituent elements in their standard states at 298 Kelvin and 1 atmosphere pressure. I want you to take note of all the terms that I've underlined here. So the enthalpy change when 1 mole of a compound, any compound whatsoever, if you have CO2, that's a compound, you must be talking in terms of 1 mole of it. And then you will have to talk in terms of all the constituents, C and oxygen. They must be in their standard states. That is 298 Kelvin and 1 atmosphere pressure. When you have that condition, for the reaction that leads to the formation of any substance, 1 mole of that substance is formed. Then the enthalpy of reaction can be expressed as enthalpy of formation. But don't forget, these are standard conditions. So the standard enthalpy of reaction will be the same as the standard enthalpy of formation. So how do we define standard states? For a gas, I'm sure you know this before now, that the standard state is the pressure that's exactly 1 atmosphere. And for a substance in solution, the standard state is a concentration of exactly 1 molar at an applied pressure of 1 atmosphere. For a pure substance in a condensed state, be it liquid or solid, the standard state is the pure liquid or pure solid. And then for an element, the standard state is the form in which the element exists, in which it is its most stable state under the condition of 298 Kelvin and 1 atmospheric pressure. So standard states must be clearly understood. And I want you to take your time to go through all of this. For gases, it's simple, 1 atmosphere. For substances in solution, we talk about exactly 1 molar and the applied pressure of 1 atmosphere. And for pure substances, it must be the states in which they are in their pure liquid or pure solid. And then for an element, you must consider the most stable states. So for standard states also, we know that for most elements, what you have is that they are solids, except for mercury and bromine. And then for diatomic molecules, you will find them in their standard states. Most of them, diatomic gaseous molecules like hydrogen, nitrogen, oxygen, fluorine gas, and chlorine gas. And then some of them monoatomic gases like helium, neon, argon, krypton, xenon, and rhenon. So these ones must know them. I put here a table that gives you the standard enthalpy, and you can find the standard enthalpy of formation for all substances there. You can take your time to check it. So for standard enthalpy of formation of an element in a standard state under standard condition, it is always zero. Always zero. So when you are looking at an element in a standard state under standard condition, then the enthalpy of formation is zero. Don't forget, the enthalpy of formation is simply describing the amount of heat change that occurs when you are bringing those elements together. So for an element in its most stable form, that is zero. Okay, so for example, the standard enthalpies of formation of carbon, which is in form of graphene, diatomic oxygen gas, diatomic nitrogen gas, sodium metal, and liquid mercury, all these are zero, because the formation, we know that the heat change is zero, because that is their standard state in which they occur. So I've given a few examples here. If you are forming water from hydrogen gas and oxygen gas, to form 1 mole of H2O in standard states, it means that you will need 1 mole of hydrogen and half mole of oxygen gas. And so you can determine the enthalpy of formation in this case for liquid water is minus 285.9 kilojoule per mole. Now, if you want to form CH4, the standard enthalpy of formation must always be that the product is 1 mole. So you will have 1 mole of carbon in solid form and 2 moles of hydrogen gas, giving you CH4. So the enthalpy of formation of CH4 gas is minus 74.9 kilojoule per mole. So one thing you must not forget, and I'll take you back to that initial slide, is that 1 mole of the compound is formed and from its constituent elements in standard states. So if you look at all the examples, we have the product as 1 mole. What about this other one? Formation of NO2 gas. 1 mole of it is formed from half mole of N2 gas and 1 mole of oxygen. Don't forget, they will be in standard conditions and you will form only 1 mole. If it is more than 1 mole, then you are not talking about standard enthalpy of formation. Please bear that in mind. Now, for the enthalpy of formation of NO2 is the same as the enthalpy of formation, for the enthalpy of formation of NO2, we can refer to it as the enthalpy of that reaction, because there is a reaction that is taking place there. I'm just trying to build on what you have been taught now. So this is a reaction, N2 plus O2 giving NO2. So we can say that we are talking about enthalpy of formation of NO2. And that value is plus 33 kilojoule per mole and is an endothermic reaction. So the formation of NO2 means that heat is absorbed for the process to take place. So it's a reaction and it is a positive enthalpy change that you get. Now, in all of these examples that I gave, if you look carefully, you will find some of the elements that are in their most stable condition, like carbon was used there. I did not talk about the details of how these values are obtained. You will see them as we go into other examples. Then some of these are atomic gases that are in standard state. So I've just put it here for you to know that in all of these calculations, we are taking note of the fact that the enthalpy of formation of oxygen okay, will be 0. That of hydrogen gas will be 0. That of carbon will be 0. That of N2 will be 0. So 1 mole of the product is formed in each case. So whatever calculations we have made there, these have been factored into it. So how do we apply this? But before we apply it, let's talk about the standard enthalpy of combustion. Because for combustion, which is a very common chemical process where you have substances reacting with oxygen to form products, usually giving out CO2. So you see that the standard enthalpy of of combustion of an element or compound is the enthalpy change when 1 mole of that compound reacts with oxygen to form products specified by balanced equations at standard conditions. So look at this very well. Standard enthalpy of combustion is that of an element or compound. That is the enthalpy change that is involved when 1 mole of that compound reacts with oxygen. So 1 mole of that compound must be reacting with oxygen to form products specified. So here we can see what is undergoing combustion here is C2H6, and the enthalpy of combustion is minus 1559.5 kilojoule per mole. And usually the standard enthalpy of combustion is always negative. That is exothermic in nature. I want to give time for questions, but before then, that time may not permit me to go through the examples, but you can be sure we will continue from there tomorrow. Let me take your attendance for the last time. So please listen to the attendance code. The third attendance code for today. Third attendance code for today. UCKLX, all in upper cases. UCKLX. That's the last code for today. U for uniform. C for cool. K for cola. L for leopard. X for xylophone. UCKLX. UCKLX for xylophone. X for xylophone. Okay. I don't know if you have any question. We can take the next 5 minutes or thereabout to attend to your questions. And some students are asking for the second code. You give it a no. Okay. So you are free to ask your questions. I will be glad to take them. I'll be glad to take your question. I've just called the third code. Man, you talked about the standard enthalpy. Various standard states is 0. Is it only for elements or gases that is 0? Okay, thank you. Yes, when I talked about the standard enthalpy, I made you to see that it is not only for elements. You can have them for gases, and I've put the conditions here. You can have them for liquid substances. You can have them for gases. You can have them for solids. But once these conditions are fulfilled, like I put it here, if it is a gas, if it's occurring at pressure of exactly 1 atmosphere, that's a standard state. So you define standard state, and I said for standard state, elements are usually solid except uh, mercury and bromine. We know bromine to be liquid, and then some standard states of molecules that are in gaseous states have also been given. So it varies. What you need to do is to adhere to the condition. For those asking for first and second code, this is not acceptable. We took that attendance much earlier. So if you still have any question, you can ask me, but it looks like you don't have questions. So I will just jump to the exercise that I left so that we can know how to apply all that I have taught before we lose it. So I've given an example here that you have to calculate the standard enthalpy for the reaction here. Without anybody asking questions, Fe, iron oxide, is reacting with oxygen. That is a combustion process. So you can look at the enthalpy of formation of Fe oxide, and then you look at the products. You have been given the enthalpy of formation for the products, and you have been given the enthalpy of formation for one of the reactants. And so the next thing to ask is, why was I not given that of oxygen? Can I calculate it? But the question is, calculate the standard enthalpy for the reaction. Oxygen is in its standard state, and it will have the enthalpy of formation of 0. So in essence, what we are saying is that for this reaction, you have to know which ones are the products and which ones are the reactants. So you have to come back to the expression for the delta H of reaction. And that is what I have used here. So for oxygen, so if this question comes to you, the question is you have to calculate the enthalpy, the standard enthalpy for the reaction. You have been given the enthalpy of formation of the reactants and the products. That of oxygen, because it's in a standard state, that diatomic gas that I gave you earlier on is going to have enthalpy of formation equals 0. So by the time you come here and you are substituting, you know that this is for the products and this is for the reaction. I mean, for the reactants, one of the reactants. So the one for the oxygen is 0. As a result of that, by the time you are substituting, you also have to bear in mind the stoichiometry of the reaction. For this reactant, it's half, is 2. For oxygen, it is half. And then we already know that oxygen is 0. So when you come to the reactant side, the enthalpy of the standard enthalpy of formation, we mean that this is 0. And then you have 2 for the iron oxide. Then by the time you come here, you have the products, and then you have 1 mole that is formed. So the standard enthalpy for the reaction is easy to calculate, and you can see the value is negative in conformity with what we said earlier on, that for combustion it is an exothermic process. So I am going to stop here. I cannot see any question from anybody. Okay, but why is formation of NO2 endothermic? While it's a combination reaction, how can we determine if a reaction is endothermic or exothermic aside from the sign? Yes, you cannot determine if it is endothermic or exothermic except you are physically present and you can touch the reactants, the reaction vessel. You will know if it is hot or if it is cold. If it is cold, that means it's absorbing heat from the environment, and then it will be cold. And then if it is exothermic, it's releasing it. So the reaction flask can be warm or hot, but this is not expected for all reactions because you may not be able to touch the reaction vessel. Now for NO2, we already said it, that NO2 is not existing in a standard state, so it will have its own heat of formation. So please bear in mind. So where is it applied? You said something about standard conditions. It's applied because you will have to state the condition of the reaction. You may be able to say, oh, I'm not the one carrying out the reaction, but when you are calculating such things, you will be told, either you are told that they are in their standard state, or you are given the values that indicate that they are in standard states, like 298 and 1 atmosphere, 298 Kelvin and 1 atmosphere. So that will be given. Okay, why does the specific heat capacity of an unknown material has a negative sign? In that question, I told you that that substance is releasing heat. It was initially 200 degrees Celsius, and then the temperature dropped to 41 degrees Celsius, 41.8. Definitely, it has lost heat. And so, because it's releasing heat, that is why the sign is negative. Thank you. My time is up. How to see you tomorrow? Okay, what is the difference between kilojoule per mole and ordinary kilojoule? Kilojoule per mole simply means you are referring to molar quantity. That is, for each mole, this is the number of kilojoule. That is the molar quantity. And ordinary kilojoule is used for heat when you are not referring to it in terms of a particular mole of the substance. That is just the difference. The difference that you see in the unit is an indication that you are referring to 1 mole of that substance when you say kilojoule per mole. Thank you. Have a great day and see you tomorrow. Thank you, sir. Let me.
Hey, ètò fún ẹ̀ ṣe sí